So I'd like to speak for a few minutes today about why the cloud infrastructure demands efficient storage models. Cloud providers need two different kinds of storage. The one we've been calling cloud storage is really for the bulk storage of files. It's good for archives, backup data, for running applications like file synchronization and sharing, for running collaborative applications like Google Docs. Basically, this form of storage works well where WAN latency masks storage system latency. So while it's important to have throughput and to have a lot of aggregate performance, the time it takes to retrieve a single file can be relatively large, maybe as much as a second. A solution has evolved for this kind of storage, and that's the object store. Products like OpenStack Swift's, Caringo's CastStore, Scality's Ring, and the like allow you to build massive object stores at a reasonable cost using off-the-shelf servers to build that infrastructure. If you're going to run applications in a cloud compute environment, you also need some sort of block storage for those cases where storage latency matters, where the difference between 1 or 2 milliseconds and 5 or 10 milliseconds of latency to retrieve a record for a database is going to have a huge impact on application performance. So cloud-hosted applications, virtual machine hosting, databases, and the like. This is what traditional enterprise cloud storage was designed for, but for the cloud provider, enterprise storage is only a partial solution because the needs of cloud providers and of enterprise users vary substantially. How do cloud providers' storage requirements differ? Well, first of all, they have different performance patterns. Having a large number of virtual machines or guests or applications or users on a single server means that the I/O patterns are denser because we've segregated the file storage to an entire different class of devices, not just to lower speed spindles in the same array. The number of IOPS per gigabyte are higher in the cloud environment. And cloud environments, because of their multi-tenant nature, need performance fairness. If some of the minor applications in a corporate environment run slowly every Thursday afternoon because the payroll application is running and it's a very high priority task, well, everybody else in the corporation knows their paycheck is getting cut, and they're not as demanding that their applications run at top speed. Noisy neighbors are acceptable when those neighbors are your coworkers. Noisy neighbors that suck up storage resources and storage performance in a cloud environment are other customers, and now that variation in performance caused by noisy neighbors becomes a problem, and it's not the end customer's problem to solve. He's just going to demand that you deliver the performance you promised in the SLA. Cloud environments are much more dynamic. It's kind of typical in a large enterprise data center that provisioning a new server or the storage for a new server is a 10, 15, or even 30-day process. Cloud customers aren't going to wait 30 days to get their new application provisioned. They want to place an order on the web Monday and be up and running by Wednesday. Then there's the funding difference. Enterprise data centers get their funding at the beginning of the year in the form of a budget. 100% of what they plan to spend that year is available. It might be broken up across quarters, but they know what their funds are going to be available. In the cloud environment, as you make sales and bring on more customers, more funds become available, and therefore increasing utilization and therefore reducing costs boosts the profits of the cloud provider. Finally, cloud data centers are 7/24, 365 environments. You have vastly reduced maintenance windows. You can't send out an email saying next Sunday at 2 a.m. we're going to be down for several hours as we expand the storage system. So this dynamic, elastic environment has different requirements than the enterprise environment does. The enterprise guys, when they manage their storage, first of all, vastly over-provision. Typically, you'll see that the real data on a large storage array like an EMC Symmetrix is somewhere on the range of 30 to 40% of the capacity of that system, in part because there are poor tools and procedures that take a long time, so that administrators do static allocation and they over-allocate space so that they don't have to continuously make changes manually. Secondly, performance in a traditional storage array is managed by physical disks. And so if I have an important application, I may give it a dedicated pool of spindles so that that application's performance isn't going to be affected by other applications' performance. I'm going to set it to RAID 1 so that I get the maximum number of IOPS. I'm going to give it a lot of spindles, regardless of what its capacity need is, thus short-stroking those disk drives using only a portion of their capacity, which improves performance, but using a portion of their capacity reduces utilization. That's not efficient, and that increases costs and therefore reduces profits. In addition, enterprise storage environments are conservative and change-averse. Doing things the way we always have done it is a good reason in that environment, and so they tend to be locked into existing vendors and existing storage techniques and storage protocols like fiber channel. So if I was going to build a block storage system for cloud providers, the first thing I would have to do is build the management differently. It's going to have to be automated and automatable system management. Just having a nice graphical user interface, especially a nice Java graphical user interface, if there is such a thing, and a command line interface that you can access through Telnet aren't going to cut it. The administrator of this system needs to be doing repetitive tasks frequently and quickly. Secondly, we need to be able to do better performance management than just seeing what the average latency is across the array as a whole. I need to be able to see how much of the available performance is in use, and most importantly, I need to be able to see and manage how much performance each tenant gets so that I can guarantee that my service level agreements with my customers are met. So the system needs to be fast enough to meet those SLAs, and it has to be predictable and controllable enough to always meet those SLAs. Cloud customers can walk if they get bad performance hosting their VMware machines on your cloud data center. They can just move to somebody else. Corporate users today don't have that choice. In the future, they will have that choice to move from the corporate data center to cloud providers, but there are still going to be political things blocking that transition. Finally, the system's going to have incremental scalability. To get good performance on a large system from enterprise storage, you have to make a very large upfront investment to buy a system capable of growing to 500 terabytes or a petabyte of space, even though you're only putting 50 or 100 terabytes in it today. In the cloud environment, you need to be able to start small at a small cost and build that system up incrementally so that your costs and your income align, again, maximizing profitability. Management needs to be efficient. It needs to, because efficient management means less staff, and less staff, of course, means more profit. Storage management alone isn't enough. Managing the storage system has to be tied in programmatically to the server provisioning process. It needs to be tied into the network monitoring process so that you have one dashboard that shows the condition of server storage and the network, and then the reporting has to be able to feed back data that can integrate with your billing system. We have to be able to do all of this without bringing in another huge dedicated management platform. CA Unisphere and HP OpenView Network Node Manager taught us that huge overriding management platforms are much more consultant-friendly than they are user-friendly. The implementation costs and continuing overhead are just too large. Having a scripting API is good, but most enterprise systems that have scripting APIs really have scripting APIs for a single scripting language. If they're targeting Windows users, they'll support PowerShell. If they're targeting open source Unix or Linux systems, it might be Perl or PHP. Better if we have a REST API that can be scripted from any language. That makes it easier to integrate with your other tools using the languages that they integrate with well. And then there's the matter of efficiency. The more efficient your storage can be, the less storage you're going to need to buy. And there are several technologies that improve storage efficiency. Thin provisioning that doesn't actually allocate storage space to volumes and therefore to users until they write to it. Often people building infrastructure and building applications will be somewhat optimistic about how well that application is going to be accepted and will demand that they have the capability to expand that application beyond the level to which it may grow in a short period of time. Data compression and deduplication reduce the amount of space any given set of data takes on a set of disk drives. These features appear in some enterprise systems, and some enterprise arrays might even be able to say that they have thin provisioning and compression and data deduplication. But these features have been bolted on to existing array architectures, and that limits their effectiveness. You won't get compression as good or deduplication as good, and those systems tend to slow down when they're fully utilized. So as we boost utilization, we may be sacrificing performance. As a result, even users that have systems that include storage efficiency functionality don't always use them. I've seen market research that indicates that somewhat less than half of the users that have these capabilities available to them on enterprise arrays actually turn them on for fear of the performance impact or other negative ramifications of implementing that. So thin provisioning clearly boosts disk utilization. Instead of allocating 100 gigabytes to a volume, and whether the user writes 5 gigabytes or 1,000 or 100 gigabytes to it, we can say, we're just going to set a quota on this volume. We're going to say it can only grow this big, and disk usage grows only when it's actually being written to. Since you get to charge your customer based on how much data they're storing on the system, that means that costs and revenue are aligned. However, in some of the traditional arrays, the process of thin provisioning is quite granular. At least one major system from a 3-letter vendor allocates space in 1 gigabyte chunks. So the minimum actual disk utilization is 1 gigabyte, and it's always going to take a multiple of 1 gigabyte. If a user uses a gigabyte and 1 bytes, he's going to get 2 gigabytes of disk space. The other problem is that traditionally thin provisioning allocates space as data is written, but when data is deleted, the space it used to occupy is still allocated to the volume, to the server, and to the application that used to use it. So we need to add space reclamation. Space reclamation is a great idea, but some vendors' implementations rely on host systems behaving in certain ways, such as zeroing out blank space when files are deleted, and Windows doesn't do that because Windows is trying to preserve those old files so that you can undelete them if you need to. In addition, zeroing takes IOPS on the disk back end, and with flash systems, because flash has a limited write endurance, actually writing zeros across a large block of flash could reduce its life. Finally, VMware, in their VAAI, VMware API for array integration, implemented Unmap, a way to do space reclamation, but some disk arrays, when they received an unmapped command, would go away for minutes at a time, and so they temporarily withdrew that, and vendors are working on improving their reclamation process. Systems designed to be efficient from the beginning will be able to do reclamation much less problematically. Compression for storage guys always comes up as, well, the tape vendors always told us that data would compress 50%, and sometimes it would and sometimes it wouldn't. How much data compresses is very much dependent on the data. Databases are quite compressible. You'll typically see a 60 or 80% or even more rate of compression for database data. VM images are somewhat compressible. They'll compress 30 to 50%. Media files and the like are frequently already compressed, and compression won't save you very much disk space. Users with experience with old systems will sometimes be afraid of the performance hit compression might introduce, but today's CPUs are optimized for compression. Compressing small blocks will reduce the latency impact of compression to the point where it's unnoticeable. Having smaller granularity will also increase compression's effectiveness. EMC and NetApp compression, because it works in a system that has fixed size allocation blocks, we can only save space if it saves a whole allocation block. And that leads to up to 15% of blank space being stored even in compressed files. If you extend compression all the way into the RAM cache of your system, then compression will not only improve storage efficiency, but it will also improve the cache hit ratio and therefore performance. Data deduplication, like compression, is data dependent, but very often the data that didn't compress well will deduplicate well, and vice versa. For example, if you have a large virtual server farm, many of those virtual servers are going to be running the same operating system and therefore have data commonality at the coarser-grained nature that deduplication operates on. So virtual machine farms will typically deduplicate 5-to-1 or better. If you do deduplication in line, that is, deduplicate as data arrives at the system, you can maximize system utilization. And again, like compression, if it extends to the cache, you can extend the cache hit ratio. Some vendors, however, limit the realm upon which their data deduplicates to a single volume. If the system administrators have decided to have multiple volumes for any reason, frequently to maximize performance because they're managing performance by the number of spindles per application, that data won't deduplicate with data in another volume. So we may have multiple copies stored on the same storage system across multiple volumes. The traditional problem with data deduplication is it turns sequential reads from the deduplicated data store into random reads. And because disk drives have to move the heads for random reads, users are afraid that that's going to create a performance issue. Performance is, of course, still important. Every couple of years, Intel comes out with a new generation of processors, and that generation of processors is somewhere from 50 to 400% faster than the last generation of processors. However, since the introduction of the 15K RPM drive in the year 2000, disk drives haven't been getting faster, and so we make systems built on mechanical disks faster by adding more disks. HP, when they run their SPC1 benchmarks, in the year 2000 would have 180 disk drives being driven by one server. With the Westmere generation of servers, they got up to 1,000 disks from a single server. With their new Gen 8 Romley-based servers, they think they're going to need to have 1,000 disk drives so that the disk I/O would match the compute performance when running that benchmark. Today's solution to performance is not just to throw more disk drives at the problem, but to introduce flash solid-state disks. Flash is substantially faster than disk. A 15K RPM disk has somewhere between 2 and 6 milliseconds of latency, can deliver about 170 I/O operations per second. A mid-range flash disk has latency of around 75 microseconds and can deliver thousands or tens of thousands of I/O operations. However, flash is substantially more expensive than disk on a per gigabyte basis. Remember, flash is substantially less expensive than disk on a per IOP basis. Today's flash is a stored charge device, and flash devices have a limited write endurance. The more times you write to a given page, eventually it's not going to retain that data anymore, and so we need to, when designing a system, manage that write endurance. So today what we see in most data centers and in the minds of most IT guys is that flash should be dedicated to high-value applications. So if you go to any of the major array vendors, they'll be glad to sell you SSDs, and you can insert SSDs into their existing array. But the architecture of that array, just like it limited the efficiency of deduplication or compression, also limits the performance that you can get from the SSD. SSDs provide data so quickly that the limited number of back-end fiber channel loops or SAS connections from the controllers to the disk trays are quickly overdriven, so you can only put a small amount of solid-state disk in even a very large disk array. Using an all-flash logical disk is expensive, and so vendors have started using flash as cache or as sub-LUN tiering, where they move hot data from disks to flash. But both of those techniques are the equivalent of driving your car by looking in the rearview mirror. It's deciding what data needs to be accelerated based on past performance, and as all the mutual fund commercials have taught us, past performance doesn't promise anything about future results. Finally, if you have one busy host, it could claim a substantial amount of the cache or sub-LUN tiering pool, so you still have the noisy neighbor problem. The solution is to combine solid-state storage and storage efficiency. Just like chocolate and peanut butter, these are two great tastes that taste great together. By using the appropriate set of storage efficiency tools, you can get high utilization. If you include substantial data reduction via compression and deduplication, you could actually end up storing 50 or 100 terabytes of data on a 25 terabyte storage system. because Flash is just as fast at random I/O as it is at sequential I/O, the drawback of deduplication, that it turns sequential I/O into random I/O, has no performance impact on an all-flash system. So if we can get 3, 4, 5 to 1 greater efficiency out of the system, then we could deliver performance substantially better than a system based on 15K RPM drives at a cost comparable to that system based on 15K RPM drives. Deduplication, because it reduces the amount of data that you're writing, extends flash life. So how do we build efficiency in rather than bolting it on? Well, first, we compress and dedupe on ingest. That is, we do these processes as soon as data arrives at the storage system. If they were post-processes, we would need a landing zone, additional storage space to hold the data until it was deduped and compressed. We need to increase RAM efficiency, and by compressing and deduping immediately upon receiving the data, we do that. And deduped data doesn't have any process it has to go through for reclaiming blocks full of zeros. It just sets the pointers for that file system to point at the one block of zeros in its block pool. We need to be able to scale the controller so we can get performance out of a system when it's fully utilized, similar to what we get when it's only partially utilized. Finally, we need to optimize the data layout for flash. We need to reduce the write amplification, that is the increase in the number of writes to the actual storage device, whether it be flash or disk, that features like parity RAID create. And by optimizing the data layout, we can wear level, that is, you put the same amount of write traffic on every cell of every SSD, not just across a single SSD, but across the system as a whole. Well, that completes my presentation for the day. I'd like to hand control off to Dave and hear how SolidFire is advancing the way the world uses the cloud.
Great. Thank you, Howard. We'll have Dave take over from here, and I'll just pop up his presentation and switch over to that one.
All right, thank you, Howard. That was just a great introduction and overview of some of the big challenges that folks face building large storage environments for cloud computing, as well as some of the interesting opportunities that solid state presents in that environment. So I'm going to spend the next few minutes talking a little bit about how SolidFire views that opportunity, the things that we're doing for that market, and essentially how we're leveraging some of those trends that Howard has talked about to really advance the way the world uses the cloud. And that's really the mission of SolidFire, is not just to build a great storage system, but to really enable businesses to run more and more of their application workloads in a cloud environment, and do that by improving the way that the storage layer works in the cloud. So the question is, the obvious question is, why don't all applications run in the cloud today? Why do people continue to run things in their own data centers when they can have potentially more scalability, more efficiency, and easier management in the cloud environment? And certainly one reason for this is that the cloud is just not viewed as ready for business critical applications today. There's concerns about security, reliability, availability, performance. And the limitations of storage are a huge part of that problem and that perception. It's very easy for cloud providers to provide a lot of cheap storage that doesn't have much performance, and the object storage environments that are out there today are certainly one manifestation of that. But if you need high levels of performance, you probably are going to look to a dedicated storage environment, and that either isn't available in the cloud or is extremely expensive for a service provider to set up a dedicated environment for you. And when you move into a multi-tenant environment, the performance ends up being highly variable, as Howard talked about. At the end of the day, it really comes down to the fact that businesses can't really replicate the consistency and control that they have in their enterprise data center, and that's a huge barrier to more widespread adoption in the cloud. So if we look at the types of application storage that are available in the cloud today, and what options enterprises have that may be looking to move their applications to the cloud, there's really just a couple of options available. So the first is direct attached storage. You can have storage directly attached to your compute instances where you can store your data, but that comes with limited capacity and performance. Whatever is in the box is what you have. Obviously, there's no high availability. If that machine goes down or becomes unavailable, then that data is unavailable as well. And you've got limited flexibility there. No easy way to move workloads between machines, no easy way to share data between machines. It's really locked up inside that box. As Howard mentioned, we also have these large object storage environments, which are great for backup and archival, but really not well suited for primary storage. If you want to run the types of applications that are listed at the bottom of the screen, database applications, business applications, you really need some high-performance block storage. And so that really brings us to kind of the network-attached and SAN-attached storage offerings that are available today. And those systems, while they may provide a good amount of capacity and a good amount of performance overall, they're very challenging to use in a shared environment because you have no performance guarantees for individual applications. They're extremely costly and complex to manage. They were designed for a very different environment inside the enterprise. Putting them in a large cloud environment really is taking them out of their element. And there's also difficulty in terms of security because, again, they were designed for an enterprise and have security features that were really designed around the needs of an enterprise, not the security needs of a large multi-tenant cloud. So the vision for SolidFire is really to address a lot of these shortcomings of traditional storage offerings in the cloud by giving service providers the ability to guarantee performance to thousands of applications at the same time. Offer quality of service to their customers with firm SLAs so that customers actually know what kind of performance to expect. Be able to provision storage extremely quickly and deploy new storage into their data centers extremely quickly without having time-consuming deployment and management processes that require manual intervention. The ability to get to very large scale within a single management domain, potentially petabytes of storage, with a single point of control as opposed to having islands of storage all over the place. The ability to give complete automation and control all the way down to your end users if you want. The ability for customers to go to a web portal and provision storage and provision capacity and modify performance and view reporting of their storage performance and take action against that is really kind of what the type of control customers are ultimately going to need to have the same comfort level that they do in their own data centers with storage systems that are completely under their control. And at the end of the day, it's really about giving service providers the ability to differentiate their cloud offerings based on cost, quality, and really the breadth of services that they're offering in their storage portfolio. And so that's why we think it's really time for a new direction in storage, and that's really what we've been focusing on at SolidFire for the last couple of years, is building a storage system that is designed from the ground up to run business-critical applications in the cloud. So if you take a look at what SolidFire is building, it is an all-solid-state storage system designed specifically for the needs of large-scale cloud computing environments, particularly like those found in cloud service providers. The system is a clustered scale-out solution. You can combine up to 100 individual 1U nodes, which gives you over a petabyte of capacity and around 5 million IOPS of performance. It uses all industry standard hardware, nothing proprietary in the architecture of the hardware. 10 gigabit Ethernet is the interconnect, and we export all the storage over standard iSCSI. But I think the bottom line here is the most interesting thing, which is that using a lot of the efficiency techniques that Howard talked about, we're able to drive a usable cost per gigabyte that's similar, or in many cases less than, a disk-based SAN, while having significantly better performance and the ability to manage that performance in ways that have never before been possible. If you look at the core functionality that SolidFire offers, it really breaks down around a couple of different areas. The first is scale, the ability to deploy a very small footprint and then add more nodes as you need more capacity and performance. Allow you to grow your cloud environment and grow that storage environment as customers come into that environment and as applications need more and more storage, rather than having to put a large footprint of storage in up front and then slowly fill that storage in up over time. And so you're able to align your expenses much more directly with the utilization of that storage and the revenue that's coming in for it. The second big focus for us is this capability we call performance virtualization, and this is certainly one of our trademarks. It's not necessarily what we're talking a lot about in this webinar today, but it's the ability to separate capacity from performance in the storage system and dial in exact specific levels of performance for each tenant in the system. So you can have large volumes with a little bit of performance or small volumes that gets tens of thousands of IOPS, and be able to, more importantly, guarantee that performance day in and day out, regardless of what else is going on in that storage system, regardless of what other customers are doing on it, and have the ability to dynamically adjust that performance up and down as application performance needs change on a customer-by-customer basis. One of the other core focuses for us, and what we'll be spending a lot of time on today, is talking about the efficiency. We call it profitable efficiency because the more efficient your storage environment is, the more profitable your storage offering will be. For service providers, it's a real simple equation. You know, how much do you pay for your storage, how much does it cost you to operate it, and how much can you sell it for? And the more capacity you get out of the storage system and the better quality that capacity is, the better performing it is, the more consistent it is, the more you can charge for it and the more profitable it will be. And so the technologies that we've built into the system to drive profitable efficiency ultimately give you a better storage offering for both you and your customers. The last big focus for us is on automation, designing a system from the ground up to be highly automated and used in highly automated environments where scripting and automation and control frameworks are the norm, not armies of storage administrators like you might find in an enterprise. We really have designed this system first and foremost for use in automated environments and done a lot of work to integrate the system with cloud management frameworks and cloud stacks like VMware and OpenStack to make it very easy to plug in into service provider environments. But today I want to focus more on the efficiency side of things and really expand on some of the things that Howard mentioned and really talk about how they come into play with the SolidFire system and how we use those technologies to drive extremely high efficiency in the storage system. When we look at efficiency, we really break it down along two areas. The first is utilization. How much of your capacity that you're purchasing are you actually able to utilize? And in a traditional storage environment, you purchase a lot of capacity, and then you lose some of that for redundancy, you lose some of that for spare capacity, you potentially lose a lot of that for overhead or because you just can't tap into it from a performance perspective, and you end up with a relatively low amount of usable capacity. With SolidFire, because of the balance of capacity and performance that we bring, because of the scale-out capability of the system that allows you to easily expand as you need to grow, you can get much higher levels of storage utilization than you would in traditional storage systems. So 80 or 85% storage utilization potentially versus maybe 25 or 30% with a traditional system. But we go much further than just increasing the capacity utilization. We actually give you more usable capacity using data reduction technologies like deduplication, compression, and thin provisioning. And I'll talk a little bit more in detail about how each of those work. But really, the key thing to understand here is that you can actually have an environment now where you can go out and sell more capacity than what you're purchasing because we're able to store more data in less space and allow you to be much more efficient with your storage utilization. The net result of these two things at the end of the day, the combination of high capacity utilization with data reduction technologies, is that you get a drastic reduction in the power, cooling, and floor space requirements for your storage environment. So not only is the cost less coming into it, the operational costs are much lower over time. So I just want to take a quick look at how we break down the data reduction technologies that we use and kind of the benefits of each of those. So obviously these technologies all reduce the amount of storage capacity you need. They have a couple of other aspects in common as well. So first of all, we execute all of these technologies inline and system-wide. So they run across the entire data store in real time as data is coming to the system. They work on a very fine-grained block size. So Howard mentioned some systems do thin provisioning on a 1 gigabyte block size. We do thin provisioning on individual 4K blocks, as well as our compression and deduplication. So you get the highest level of efficiency from these data reduction techniques. Third thing is these are always-on technologies. These are not things that you can turn on or off to trade capacity for performance. They're always on because they were designed into the system from the beginning. They're not something that we can just flip on and off. They really are designed to be always running all the time across all of the data. And the other reason we always have them on is because they actually give performance benefits rather than hurting performance. So deduplication and compression, as Howard mentioned, can actually reduce the amount of I/O that you need to do to disk and increase the amount of data you can store in cache. We do our compression and deduplication in a way that we don't create hotspots in the storage, so you don't have kind of odd latencies because some data is highly deduplicated and shared and some data is not. The thin provisioning technology we use really has no performance impact whatsoever, which is one of the challenges that a lot of thin provisioning technologies still have even today. And we don't have to use space even within applications when they pre-allocate or write zeros to data. We don't consume any space for that. So very, very efficient when it comes to the thin provisioning as well. And so taking these technologies, I want to take a look at how we view the benefit that these technologies bring in an actual customer environment. So we're going to use a scenario here where we say, let's say that we've got 100 terabytes of primary storage that we've gone out and sold to customers in a cloud environment. How much storage do we actually need to buy to provide that to customers? So we'll start by looking at how much we're provisioning for customers versus how much space we actually utilize. So of that 100 terabytes that we've sold to customers, some amount of that is going to be used immediately, some will be used at some time in the future, some will probably never be used even though they've purchased it because nobody tends to fill up their disks to 100%. So of that we can get some savings through traditional thin provisioning, just not allocating space to blocks that haven't been written. So in a traditional storage array you might be able to get that space down to 60 terabytes or so of actual utilized space. As we mentioned, SolidFire's thin provisioning is quite a bit better than traditional storage because we use 4K block sizes, because we can reclaim space and actually reclaim space within applications. We actually think we can do a little bit better than that. So maybe with SolidFire you've got about 50 terabytes of storage that's actually utilized. Now with the traditional storage array, this is probably about as far as you could go is thin provisioning. With SolidFire, this is really just where we start. So we take that thin provision data and we compress it. And as Howard mentioned, compression ranges can certainly vary depending on application and data type, but across a wide range of data, 2-to-1 compression is pretty typical. So we take that 50 terabytes or so of data and compress it down to about 25 terabytes of actual data. We then take that compressed data and deduplicate it. And the amount of savings you get for deduplication can also vary. We actually have tools that can help you look at these rates in your own environment. We think a very conservative estimate across a wide range of data in a cloud environment is about 2-to-1 deduplication. So we take that 25 terabytes of compressed data and deduplicate it down to just under 12 terabytes or so of unique data. So essentially what we've done here is taken that 100 terabytes of space that's been provisioned and sold to customers down to 12 terabytes of data that we're actually having to store. And a significant savings versus what you would get even with a thin provisioned enterprise array. Now of course this isn't the whole story. What you have to store isn't necessarily what you have to purchase. And so we'll take the bars out the other way and look at how much space are you utilizing versus how much capacity do you need to actually provide that space. So again, we'll start with the traditional SAN environment. In this case, we have that 60 terabytes of utilized space after thin provisioning. We add in the overhead for redundancy. Obviously, there's different levels of RAID. We're going to use RAID 10 in this example because, again, assuming performance is important, that's typically what people will do. There may be system reserved or snapshot reserved space that you have to account for, but the big question mark is underutilization. As we talked about earlier, it's very difficult to use 100% of the capacity that you're purchasing in a disk storage environment because of the performance limitations, because of the other issues that you have to account for, like growth within the storage system. And so there is going to be typically some amount of it that's underutilized. And that amount will certainly vary depending on your performance requirements and the particular storage architecture that you're using. But at the end of the day, for that 100 terabytes that we've gone out and provisioned and sold, we could be purchasing anywhere from 120 to 360 terabytes or more of raw capacity. With the SolidFire system, we're obviously starting with a much smaller amount of storage that we're utilizing. We, of course, have overhead from our redundancy mechanisms, which we're not going to be able to get to in this presentation today, but we have some great technologies called SolidFire Helix that can protect data while having a very minimal impact on performance, even in failure conditions, which is extremely important for a service provider. So we take the overhead from our redundancy mechanism. We don't have any snapshot reserve or system space or anything like that. And we're certainly not going to claim you can run the system at 100% utilization. But again, we think it's much easier to get to 80 or 85% than you would be with the traditional storage array. So the net result is for that 100 terabytes that you've provisioned and sold, you're actually only needing to purchase 25 to 30 terabytes of raw capacity. And so you have a significant savings here, anywhere from 5 to 11x savings of the capacity that you need to purchase versus a disk-based array when you're looking at raw capacity. But also, if you think about the power, space, and cooling that you're saving as well, your operational costs will be dramatically reduced over the lifespan of that system as well. And by the way, the system is going to have about 10 times the performance with the ability to guarantee that performance to individual applications. So a dramatically different view in terms of what you can deliver out of the storage system. I just want to take a quick run through at looking how under the covers we deliver some of these capabilities, because this is really cool stuff. We have some really interesting architecture that enables us to do this. This isn't really meant to be an architecture deep dive, but I want to take a quick look at that, and then we'll get into some question and answer. If you look at the way the first kind of SANs, the first block-based storage systems were designed, the idea was basically get a big pool of disk and run RAID over it, carve that up into individual LUNs or volumes and export those over the network. And the storage controller basically did a very simple mapping of virtual address space in the LUN to physical blocks in that disk pool. And there wasn't really a lot of science involved, and it didn't really make great use of that capacity, but it did enable that capacity to be shared by many servers, which was really the initial goal of network storage. The next generation of SAN technologies, starting with guys like Compellent and 3PAR and Data Domain, or Equalogic, would get a little bit smarter about how they manage that capacity pool. Instead of managing a LUN as a single capacity allocation, they would break it up into smaller chunks or extents, could be anywhere from a megabyte to a gigabyte in size, and place those chunks or extents at different places within the disk pool as data was written to them. And this is really where the thin provisioning capabilities of these arrays came from. They wouldn't allocate chunks to specific address space until data was actually written there, as well as the capability to do storage tiering or sub-LUN tiering, because they could move these chunks of data between individual storage pools. So some cool functionality that came out of this, but at the end of the day, you still have this one-to-one relationship between blocks in virtual address space and blocks on disk. And that relationship, which is really intrinsic to how these controllers work, make technologies, efficiency technologies like compression and deduplication very challenging, because they break that direct one-to-one relationship. So if you look at how SolidFire is architected, we've taken a very different approach. We've completely separated what we call the volume metadata, the representation of which blocks belong in a specific volume, with the actual storage of the data. We separate that into a separate system we call the block data storage system. And what that allows us to do is completely optimize how we store the data in the block data system separately from really worrying about which blocks belong to which volumes. So things like compression and deduplication can be inherently built into how we store the data without having to worry about this one-to-one mapping of virtual blocks to physical blocks. The other thing we can do with this is spread the block data very evenly across the storage system to keep the load on the storage system extremely balanced, preventing hotspots from developing, and also allow individual volumes to harness as much or as little of the storage system's performance as they require. And this is really a key facet of our performance virtualization capabilities that we talked about. So again, this is just a quick overview of how the SolidFire storage architecture works. We'd love to walk through it with you in more detail on a one-on-one basis if you'd like to know more. So that's been hopefully an informative run-through of SolidFire in terms of the architecture, the direction that we're going with the system, and the capabilities we have, particularly in the area of efficiency, to deliver a profitable and differentiated storage system to service providers. At the end of the day, our goal is to really expand your competitive capabilities, expand the quality and functionality of your cloud environment, and allow you to help us advance the way the world uses the cloud. For us, it really goes beyond just delivering a storage system. We are really designing this technology and this company to help you fuel new opportunities for your service and your customers. And we really think that the SolidFire technology can be a cornerstone in helping you do this. So with that, I will open it up for questions. I don't know if there's been any submitted yet, but we'll let Adam pick it up and share any of those that have come across.
Thanks, Dave. I've got a few questions here, but as I open these up for Dave, and if some of them end up being for Howard too, please do continue to go ahead and submit questions if you've got more of them on the Q&A tab, and I'll try to keep an eye on that as we go through these. So real quick here, good one was asking how can you plan how much storage you need to actually purchase when taking this dedupe and compression into account?
Yeah, that's a great question. Obviously, because compression and deduplication rates can vary, it can add a little bit of uncertainty into the question of how much capacity do I need today and how much will I need tomorrow. So we do a couple of things to help you with that, one of which is that we have a tool that we call the eScanner. This is a tool that we can actually give to you. It's free of charge. You can run it against your current environment. You can run it against data sets that you already have in place, and you can get an idea of essentially how much capacity can be saved and how much capacity would be required to store that same data on SolidFire. And that'll give you a great kind of set of starting points and working guidelines to work with. And then over time, the storage system itself provides a lot of data, a lot of reporting out of it on efficiency and efficiency trends and storage utilization trends, so you can see on a kind of predictable, manageable basis where your capacity growth is, both in allocated capacity as well as utilized capacity, and kind of how you need to grow in terms of your storage environment. And because it's a scale-out system, it's very easy to incrementally add capacity and performance as you grow, rather than having to worry about putting it all in up front.
Okay, another good question here was asking for some more information about what kinds of things you can actually automate through the API, or are there pieces of the storage that, you know, are, what does the API cover is basically what I was asking.
Sure. Yeah, so the REST-based API, which is really at the core of the storage system, is completely comprehensive. Absolutely anything you can do with this storage system from the second you plug it in can be done through the API. So deployment of the storage system, expanding, adding capacity to the storage system by adding more nodes to a cluster can be managed through the API. All of the day-to-day provisioning and management tasks in terms of provisioning customers and volumes and accounts can be managed through it. Everything you need to manage the performance capabilities that we talked about through the storage system, and then all the reporting, all the kind of usage information, the reporting information, error handling, billing information that you may want to get out of the system to actually charge customers based on their utilization. That all comes out of the system as well through the API. And we have management tools that sit on top of that API. We have REST-based, we have CLI and web-based management tools that sit on top of that, but they really are just wrappers around that API, and they don't give you any capabilities that you couldn't do yourself directly through that API.
So it's kind of a follow-on question to that. Is that asking if the API is available to customers?
Absolutely. We make it available to both customers as well as folks who are interested in potentially becoming customers. So if you'd like, just let us know, and we will follow up with you and get you access to that.
Okay, so there was a couple more. I'm actually going to ask them both because I think that the answer is going to end up being related, so I'll just give them both to you. So there was questions asking for a little more detail on how we can do dedupe and compression without affecting performance. And a good follow-on to that that was asked was, what kind of performance hit do snapshots have?
Okay. Yeah, so the compression and deduplication question, you know, our ability to do that without impacting performance really comes down to a couple of key aspects of the system. So the first is the SSDs themselves. As Howard mentioned, compression and deduplication actually both have the effect of randomizing I/O patterns. And on disk, that's going to seriously hurt your performance. On flash technologies, if you do it right, that can actually enhance your performance because you have multiple I/O channels that you can pull from, even on an individual SSD. And so those technologies, when implemented properly, don't have to hurt performance at the disk level. Now, if you look at the higher system level, Another place that can become a big bottleneck is the CPU, because compression and deduplication and the hashing that goes along with that does require additional CPU, and that can quickly become a bottleneck in a kind of traditional storage controller and disk shelf architecture. Because our system is a true scale-out architecture, as you're adding capacity, you're getting more CPU, more memory every single time you do that, and we can keep all of those things in balance and ensure that we don't become starved for CPU even as your capacity requirements grow. Snapshots, the question about snapshots is a great one as well. We can definitely do snapshots very well. We can do it without a significant impact on performance, and it really comes down to the way that we've separated the metadata storage from the actual data storage. When we take snapshots, we make very thin copies of this metadata rather than actually touching the data itself. And so we don't need to use redirect on write or copy on write or some of the other techniques that have traditionally been used for snapshots in storage systems that tend to have a pretty heavy impact on performance. And again, those techniques are primarily used because there's this one-to-one relationship between virtual blocks and physical blocks. And when you take snapshots and you're trying to share some of those blocks between different virtual views of that data, it kind of messes with that paradigm. And so they have to take some extra steps in order to maintain extra mappings and be able to copy data to different places to make that work. Because we've completely separated the metadata from the data, we can just make direct copies of that metadata, and we don't have to mess with the blocks on disk at all.
Thanks, Dave. That's actually, so puts us at the top of the hour. I wanted to give Lena a chance to close up the call and mention that other questions that we didn't have a chance to get to, we'll follow up with those offline.
Great. Excellent. Thank you so much, everyone. That concludes our presentations for today. So we will send out a link to a recording of this webinar once it is posted and available online. And we will also send a separate email follow-up to download Howard's white paper on storage efficiency, as we promoted with the webinar invitation. So that will all be coming out as a follow-up. Thanks, everyone, for attending.
All right. Thank you very much, Lana.